before we can perform the update, we have to recover the unshifted outer product matrix. Remember, the subscript S means cyclic shift. OK， 那你要把这个除掉，所以你要反向操作。你从 O 到 OS 是用负的 i 减一个 unit 去做 cyclic shift。那你要 recover 呢，就把负拿掉，你做正的 i 减一个 cyclic shift， 你就可以从 OS going back to matrix O. Okay, but this time it's already an updated outer product matrix O prime, not just O. Okay, 它已经走了一个 loop 了 ，almost 走了一个 loop. Okay, and here is the central idea of the PCGP. Okay, according to the singular value decomposition SVD theory, the distance function will be minimized. Remember, the update for the purpose of update, we need to minimize the distance function z. Distance function means the difference between the gated signal pulse with the updated version. Okay, 你目前这一版的 A sub c 跟你要用什么样的 A of t、G of t 可以产生新的 A sub c， 让两者之间的 difference 最小哈，这个叫做 minimize distance function. And it's based on the SVD theory. It states that you can do so. The new vector A, which is represented by A prime, is equal to O multiplied with O transpose, then multiply with big A. Okay, and similarly, but slightly differently, G prime equals O transpose multiply with O multiply with G. Okay, so these two are matrix operations. Okay, just performing matrix operations. You can update the signal field and the gate field with these two formulas. Okay, this matrix O prime comes from the end of last page, right? And this is the original one. This is a new one. Okay. Then you complete one loop, and the iteration continues repeatedly until both vectors, A vector and the G vector, signal pulse and the gate pulse, converge. Converge means the Flock error does not decrease anymore. Then you can stop the algorithm. And this is so-called PCGP algorithm. It applies to blind Flock where both A of t and the G of t are unknown. You can see there is no assumption between A of t and the G of t, right? And you can get both solutions simultaneously. That is blind Flock. Okay? Any question about the PCGP algorithm? Okay. Now I offer one bonus opportunity. Is there any bug in these two formulas? Look pretty, but actually there is bug. Where is the bug? Forget about the SVD. You do not need SVD. There is no proof in here. But you can just use very basic knowledge about matrix operation. You can know there is bug there. Good. Dimension, right? What is the dimension of this matrix? N by N. What is the dimension of O transpose? Still N by N because it's a square matrix. It doesn't matter about the transpose, right? So after the product, you got an n by n matrix still. What is the dimension of vector A? 1 by n is a row vector. So can you perform multiplication between n by n matrix and the 1 by n row vector? No. So you need to transpose, right? Let me show you one example about PCGP. Okay, this is the assumed Floch trace. Okay, delay axis, frequency axis. It's a two-dimensional Floch trace. After iteration by PCGP, you got this. So they look very similar. Okay, and this figure shows the retrieved A of t, the signal pulse in the time domain. You see the intensity distribution here, a double peak pulse. Suppose the iterative Fourier transform algorithm will have some problem in this case, but in PCGP it looks pretty well. And this is the temporal phase function, okay? And either phase or intensity, actually there are two curves there. One, assumed temporal intensity, temporal phase. The other, retrieved temporal intensity, temporal phase. And you can hardly tell the difference, right? That means the performance is pretty good. PCGP almost gives you very perfect retrieval of temporal intensity and phase. 就几乎完全重叠了嘛，所以代表重建的结果非常理想。And the right figure shows the retrieved gate pulse G of t. Again, you see almost overlapped temporal intensity, but this time slightly different temporal phase, but not big. Because here the flat curve means the original temporal phase is flat, it's a chirpless pulse. And then the red curve is the retrieved temporal phase. It seems that there is only a constant difference between them. So essentially, there is no difference about the shape of the pulse. Okay, absolute phase does not change the shape. It should be unimportant. Okay, so it's a clear evidence that PCGP can do a good job in blind Floch. You can recover not just the signal pulse, but also the gate pulse. And even a two-peak pulse does not introduce much problem. Okay. But there are problems about PCGP. Okay. Say these two are the formulas we need for update. Okay. But they work only if matrix O is a square matrix, right? If it is not a square matrix, this formula does not work. Okay? And if it's restricted to square matrix, what would be the practical problems? Okay? It means Floch trace has equal number of samplings along delay and the frequency axis. Because of the square matrix, your number of sampling along tau axis has to be the same as number of sampling along the omega axis. And the number of sampling along omega axis should be the same as number of sampling along the t axis because they are Fourier transform pair. And in practice, this could be a problem, right? What is the number of samplings along the omega matrix, omega axis? It depends on your spectrometer, right? So it could be hundreds of data points. And how do you determine the number of samplings along the tau axis? Delays based on your delay line, your motorized stage, right? And usually they are different, right? If there are, for example, 200 points along the omega matrix, you have to sample your delay axis by 200 points as well. And sometimes it could be a problem, not just inconvenience, okay? For example, if you try to measure very short pulse, say your pulse width is only 5 femtoseconds, and your omega axis has 200 samplings, so delay axis also 200 samplings, but your pulse width is only 5 femtoseconds. So you can imagine d tau, the delay step size, has to be very, very small. And sometimes it could be too small to be implemented, right? Your delay scanning stage has to be precise enough such that you can have very fine resolution along the delay axis, okay? So this is a tight constraint that you have to meet, so otherwise PCGP does not work. Also, as you have seen, you have to perform cyclic shift of big matrix, and it takes a long time. In each loop, you have to perform cyclic shift many times. So you will slow down your calculation, okay? So is there any method that rectangular matrix still works and no cyclic shift is required? That could be a better choice, right? And there is. In the least square GP, LSGP, rectangular matrix is allowed. Okay, for example, your delay axis is sampled by 4 data points. Your omega axis is sampled at 5 points. Okay, 4 by 5. So it's a rectangular matrix. The sampling of signal pulse, A of t, is very simple, straightforward. You got A1, A2, A5 spaced by dt in the time domain, just like the previous case. Okay? But the sampling of gate pulse is different. Be careful, G of t is not sampled at 4 points. It's neither 5 points nor 4 points. It's sampled by 14 points, according to this formula here. Okay. 所以它到底该被取样几个点，是用这个公式决定的。Okay. The blue one is here. Number of samplings along omega or t axis is here. M is an integer. In this specific example, we choose m equals 3. And the meaning is d tau equals 3 times dt. Okay, so now d tau can be different from dt. Can be 3 times bigger than dt. So for example, if you have, say, 200 data samplings along omega or t axis, you just need 66 samplings along the tau axis. Okay, so you have some degree of freedom to modify the step size along the tau matrix. And the calculation shows you need 14 samplings along the time axis for gate pulse. Then you have to create a rectangular matrix to represent gated signal A sub 6 t tau. Here I designate the matrix as Q matrix, okay? And the element Qij is governed by this relation, okay? For example, row by row is easy. I equals 1, so you will see Ai. So first row you have always A1. Second row you have always A2. The nth row you have, the fifth row you always have A5. Okay, but the column-wise it could be a little bit more complicated. For example, the first column, when j equals 1, you have to use this formula. Okay, j equals 1, so you have 1 minus 1, this is 0. 3 times 0 is still 0, so you have just gi. I equals 1, 2, 3, 4, 5, so you have g1, g2, all the way to g5 in the first column. But in the second column, when j equals 2, this is 1. So actually you have gi plus 3. Okay, that's why you have g4, g5 all the way to g8。所以第一个 column 是1到5，第二个 column 是4到8，有 partially 的重叠，但是都是连续下来的。Then you have j equals 3, j equals 4, and you can check the first column means a sub 6 when delay equals 0, second column means when delay equals minus 3 dt, third column delay equals minus 6 dt, and so forth. So now you have a 5 by 4 matrix, which is the numerical representation of this one, a sub sig。所以你的 G 呢，其实要用到14点的取样，从 G1 到 G14 才能组出这一个矩阵。OK。Then we can skip all the steps that are similar to PCGP, just focus on something different. The only difference is the upper left corner in the flow chart from A sig prime to the new A prime. Okay? What is the idea? This is the definition. Gated signal is equal to the signal pulse times a shifted version of gate pulse, A of t times G of t minus tau. This is definition. So update could be carried out in this simple way. You have A sub sig, right? Which means you have this one. If you multiply this one with G star, what will you get? You have A times G star, so you have A times G epsilon square, right? Then how do you get A? Just normalize to G epsilon square. And for the same reason, the new G can be implemented in this way, A sub sig times A star normalized to A epsilon square. Okay, that's the idea. Then all you have to do is using the numerical representations to implement these two equations, these two formulas. Okay, so I just write down the result. Basically, just numerical representation of the first formula and the second formula. That's it. And if you do so, it satisfies the least square minimization of distance function in terms of least square method. Okay. Again, iteration continues until both vectors converge. And it also works in blind frog. You can get signal pulse, gate pulse simultaneously. Okay. The advantages are here. No square matrix, no cyclic matrix shift anymore. Okay. So you have flexible choice of d tau and d omega. And you can have faster convergence. Okay. So it could be advantageous if you use LSGP. Let me show you two examples. The first one is a polarization gating frog trace. Okay? In theory, it's like this. And if you use LSGP, you got this. Okay, they look very similar. And this is the results about gate pulse in the time domain. You have three curves actually. The gray one means theoretical curve. The blue one means the retrieved curve using PCGP. The green one means the retrieved curve using LSGP. And you can see they almost overlap with each other. Okay? So in this case, it looks like both PCGP and LSGP work well. Okay. This is gate pulse. And this is the signal pulse here. In terms of temporal intensity, the three curves still overlap with each other pretty well. And also the temporal phase curves overlap with each other. Okay, so you might feel there is no big difference between using PCGP or LSGP at this point. But if you zoom in, okay, this is the replot of the signal pulse reconstruction in the time domain. And I just look at here. I just pick up a small temporal window for zoom in observation and shown here. You can see the theoretical curve and the LSGP curve overlapped perfectly. But this time you can identify some difference between the PCGP curve from the other two. Okay. So that means in this case, PCGP is slightly worse than LSGP in terms of accuracy. Yes? Good question. I have to check with the author. These figures provided by this guy. But I think it's a fundamental difference, not because of the sampling. Okay, but I can make sure whether you are right. Okay, good. So in this case, LSGP outperforms PCGP, but it's under this condition. Your frog trace is free of noise. We did not add any noise in the frog trace. And it turns out that LSGP outperforms PCGP. Usually, you will find it. But we have also found if you add noise, which is usually true in practical experiments, right? Then PCGP is better, performs better than LSGP. So there is a trade-off. If your signal-to-noise ratio is poor, maybe LSGP is not a good choice. Okay? Then you might need to either switch to PCGP or you have to perform some noise rejection filtering before performing iteration. 你要先把你的 data trace 拿来做一些 noise suppression， 不会很难啊，就是一些简单的 Fourier transform filtering， 通常可以把很多不必要的 noise 给去掉，接着再丢进演算法。这个时候LSGP 通常就可以做得不错。Yes。可是 PCGP 看起来有没有做 noise filtering？我没有把 data show 出来哈。我刚刚讲的意思是加了 noise， 大家都不做处理，直接下去用演算法算，那么它会好一点 ，PCGP 会好一点。它既然没有做 noise filtering， 它为什么会比较好一点？这就是它演算法先天上的 advantage， 它对于 noise 有一定的抵抗能力。不要忘了，这些都是迭代演算啊。就是说 ，OK，think about why this algorithm can resist the influence of noise. You can think about if your frog trace has some noise, is there any solution that can generate the noisy frog trace? Maybe you can never find that solution, right? But the convergence requires you should get some solution, and there must be some error there. 我的意思是，你一个带有 noise 的 frog trace， 那数学上可能根本没有一个 complex function 可以产生这个 frog trace， 所以不论你怎么迭代，你也不会得到一个所谓的 unique solution， 对不对？ 但你最后还是收敛到一定的地步停下来了嘛。那现在问题就是说，停下来的时候，这个 function 当然跟有 noise 的 frog trace 是对不起来的，但它很有机会会对到一个把 noise 拿掉之后的 solution。那这个过程就等于是一个抵抗 noise 影响的过程，它是在 software 来抵抗，而不是在 hardware 先把你的 noise 拿掉。通常这个frog algorithm 会有这样子的功能所以它一定程度可以帮你抵抗 noise。有 paper 专门讨论这件事 ，How good your frog algorithm can resist the noise. And it looks not bad, even you did nothing. The iterative algorithm still help you to get some solution better than you expect. Yes?
Does this algorithm always converges?
No. And that's the experience I intend to show you in the midterm exam too. 你去写看看会不会收敛 ？Not always， 不一定都收敛，不一定啊。我其实给大家看一个 example 嘛，如果你用迭代傅立叶演算，它不收敛啊 ，error 就停在那里。可是那个 pose 跟你假设的差很多你假设 2 pick， 可是你停在3 pick， 对不对？那就是不收敛了。